Welcome back. So in this video, I'm going to be discussing the behavior of a spool, essentially, which is nothing more than a system of two concentric cylinders, one of inner radius little r and outer radius capital R. Typically in a spool, around the inner cylinder, you will find wound up some kind of rope or wire that some person will eventually exert a directed force on. This directed force could be in any direction, really. But for the sake of simplicity here in this problem, I've chosen the directed force to be precisely along the horizontal direction, as you can see on the diagram. You could have it otherwise. You could have the force make an angle with respect to the horizontal, etc. But again, I'm just keeping it simple because I just want to convey the way that you want to be dealing with these kinds of problems. Now, as with all rolling motion problems here, typically the biggest difficulty comes from determining the behavior of friction. Where is it going to be acting specifically? Is it going to be, for example, in this case, to the left or to the right with respect to our contact point on the bottom there? And it's not really obvious from the get-go. We have to analyze what happens basically from the forces outside friction, so everybody else, what they are trying to cause the system to do, and then we can safely turn our attention back to friction and make, again, a very good educated guess about its direction. So it's not going to be so much a guess by the time we actually determine what the other forces do. It's more so going to be the actual behavior of friction. So how do I get started in a problem like this? Well, the first thing you want to do is you want to see how the accelerations, the angular one and the center of mass acceleration, basically behave due to the other forces. And of course, you want to put down the actual other forces that are acting right now, ignoring again friction for the moment. What's acting on this spool besides friction then? Well, you're going to have here, obviously, gravity. That's going to have its tail again precisely at the center of mass. So that's going to be our little gravity here, capital mg. And you're also going to have, very obviously, your normal force that's holding you up from the ground. And that normal force is going to be, again, it has its tail exactly at the bottom here of the spool. And the gravity, again, has its tail at the center of mass. So I'm just making that obvious for you. And we see again, we also have the applied force, which is exactly at the inner radius, little r right now. That's where it's being exerted. And it is precisely, like we said, horizontal in this example. So these are your forces. There's really not much else except friction, of course, that's acting on this thing. And your first observation here should have to do with the stuff that's going on in the linear world. Namely, you should be able to see that right now there's equilibrium in the y direction, meaning again that n is basically going to be exactly mg. And then the only acceleration that you're going to have linearly is going to be from this force F, and it's going to be directed to the right. Namely, again, if we put some kind of axis system over here, again, we're doing this very roughly because we just want to get an idea of what the accelerations look like. We're not solving for the accelerations, obviously. So if I do that and I write down my net force statement for the x direction over here, I can determine very quickly that my ACOM, because the only force acting again in the horizontal direction is this F, my ACOM is going to be essentially F over M, and it's going to be directed, as you can see here, to the right, okay? That is precisely what ACOM is going to be doing. Now, for the angular one, we can determine it using torques, very obviously. So I'm going to leave that there for now. And then we're going to go and see again what kind of torques those forces are putting on. And again, what we want to be filling in is Newton's second law in angular form, essentially. So tau net is equal to I alpha. And again, for our spool here, we can determine eventually what the moment of inertia is going to be. I will label it over here for the time being. I will label it I, but this is something that we, again, could very easily figure out later on in the problem. So now, ignoring the moment of inertia, because we're going to get it eventually, we care about the torques. We could have torques right now from three forces, again, from gravity, from the normal, and from the applied force F. Those are the three that we could get right now. And I should mention that the size of those torques, basically we can find by taking the distance from our pivot point and to the tail of our force vectors, multiplying by the magnitude of the force at hand, and then the angle, the sine of the angle rather, that this r vector will make with our F. So this will be applied right now to all three of these, and we shall see again who contributes and what. So to start with gravity, the problem with gravity is that its tail, as you can see, is overlapping with what we're going to be taking right now as the pivot point. We're going to take the center again of the spool as the pivot point, as the spool would be rotating again about that central point when the motion goes on. So if that's the case, then the R term for gravity, the R term here for gravity, is going to be 0, regardless of if the force of gravity is mg and whatever the angle could be. I don't think you can define an angle when you're dealing with a 0 vector here. So because of that 0 distance between the pivot point and the action of gravity, we're going to get that gravity contributes no torque, basically. And when we take a look at the normal, the problem with the normal is that, as you can see, the tail is over there, and the direction is upwards for our normal right now. If you pay close attention, that's what we have right here. And the r vector that would connect the pivot point to the tail of that normal vector, again, this r vector that I'm drawing in blue here, you can see that it's directed opposite to the normal force. That is, it is directed at an angle of 180 degrees, which means when I go to fill in my normal right now, the stuff from my normal, I would get here that it's acting at a distance capital R, the force is N, but the angle, again over here, between R and N is going to be pi, which will give me a big fat 0 again. So it looks like these are not doing anything. Maybe it shouldn't be surprising to you if you've done more problems like this in the past. But again, they don't do anything for the reasons that we outlined. So the only guy left here is tau of F. What does tau of F do here? Well, if we fill in the R that it acts at, we can very easily see that that force F from the pivot point right now, let me again decrease the size of our R vector to point exactly there. From the pivot point, the distance that the force F is acting right now is just little r. So that's what we're going to fill in here. And the force itself is capital F, while the angle that the R vector and F make right now, you can see on the diagram, is going to be 90 degrees. So we put in sine of 90 right now, or sine pi over 2. Sine pi over 2, very easy. That's just going to be 1. So basically this term goes away, and you're left with just RF. So where is the actual force here trying to rotate the spool itself? Well, we can figure that out by imagining again. You can use your pen for this determination again. We can pick up this R vector over here. Basically, what you would do, you would pin your pen exactly where point P is, and you would make sure that the tip of your pen on your piece of paper crosses through the tail of F. And then what you would do is you would basically apply F. In my perspective here, I'm going to be seeing obviously the opposite of what the camera is recording here. So in my perspective here, when I apply F in this fashion, I get, in my perspective, counterclockwise rotation. If I go in the camera's point of view, again, and I pin the actual R vector like this, and I apply the force F right now to it, I'm going to see again that counterclockwise rotation from the camera as well. So the spool is trying to be rotated right now in the counterclockwise direction by that torque, which means again, we're going to be getting this kind of alpha right now. So what does this mean, right? We have come to the conclusion of what our accelerations are going to look like. That's what we wanted, right? We wanted to see what ACOM and alpha are going to look like. So I'm going to get rid now of all of the unnecessary information, and I'm only going to keep the contact point around at the very bottom because that's really all that matters at this stage. And we're going to, again, picture right now, we're going to picture the accelerations. So let's see. At the contact point down here, we have determined that there would be a center of mass acceleration that would be driving me right now to the right, like that. And I don't know the size of this right now. I have no idea, quite frankly, what the size of this is going to be because I don't have numbers that I could plug in right now and check. So what I could do here, I'm just going to arbitrarily draw a vector and say that it's going to the right. There's not much more I can do at this point. Now, with respect to alpha, you can see that it's trying to rotate my object in the counterclockwise direction. So that means for my contact point down there between spool and ground, the linear translation, when we translate the effect of this angular acceleration to the linear world, the effect is also going to be toward the right, which is very confusing, right? We're going to get here the angular, again, contribution translated to the linear world is going to be alpha r again over here. Why alpha capital R? Because again, if you remember from your arc length formula, basically right now, we can convert this alpha to a linear acceleration by just considering how far, again, this point, the contact point, is from the center and multiplying that distance with our angular acceleration to get the linear equivalent. So that distance again here is capital R, and that's why you see me multiply alpha by capital R to convert it to see what the linear equivalent of that acceleration is at that contact point. Now, I have this, and one of the choices again for friction was that it will go to the right, correct? If I put it over here right now, okay, if I put the friction to be going to the right, the thing is, what it's going to be doing is, you can see directly that it would be helping ACOM by making it grow, and it would also be helping alpha R because it would provide, again, if we put our pen again pivoted at the point P in the center, and we apply the friction toward the right, we would get again a counterclockwise contribution to the angular acceleration, and that's not good, right? Because that means friction would grow ACOM, but it would also grow alpha R. And we know that this is not what we want for rolling to occur. If we want rolling to occur as soon as the spool moves, we want basically a chance for us to be aligned like this right now, where alpha R is basically going against ACOM, and the two vectors right here, the alpha R vector and the ACOM vector, are exactly the same and pointing, as you can see, in opposite directions. This is the requirement for rolling again without slipping as soon as we start moving. So it's not good to put the friction right now to the right, because there is no way for us to ever be able to obtain that scenario. So what if I, by process of elimination, you can see got rid of the wrong answer here. So what if I did place the friction to go to the left here? How is it actually going to alleviate the problem that we have? First of all, the accelerations are both pointing in the same direction. How are they going to change direction? How's one of them going to go the other way? So here's how it can happen, and this is what usually confuses students, that this actually can happen, because friction could affect the accelerations here, each of them, differently. So for example, the contribution right now of FF to the ACOM here could be a contribution. Let's say that the acceleration contribution from the friction is basically this blue, as you can see here, this blue arrow. This could be the linear acceleration contribution of our friction. So it gives us a massive pull again to the left. But for the torques, our friction could act very little. It could be, again, the case that it provides very little torque, right? The torque effect is a lot smaller. So the alpha friction, I should say here, alpha friction R contribution could be very small. And what would that mean right now if it was very small for this guy and huge for that guy? If I sum the two vectors together right now, what I want to show you here, if I sum the two vectors together, what would I get right now? If I sum these two, I would actually get a residual on the left, which is exactly what I was looking for, right? This is about what the difference is between those two arrows right now. This is about what remains if I do this again with those two arrows. And then if I sum the arrows here, right, for the angular contributions, you can see that I pretty much get roughly a vector that points to the right with equal magnitude. And that would be your overall alpha R contribution right now. So again, the vectors here, that would be the overall alpha R after we consider friction, and that would be the overall ACOM after we consider friction again. And now I actually have the ability to roll. You see how magically this can happen? Because again, friction, it doesn't have to affect your accelerations, the angular one and the linear one, in the same fashion. It could affect one a lot more than the other one. So having friction on the left here gives us an opportunity for actually flipping the direction of those accelerations and making them again obey that rolling condition. So we know now that this could happen if I make friction go to the left because of that. So we have determined right now, after all of this discussion, we have determined that friction is going to be going to the left for sure, okay, for this to be even possible to roll immediately. Originally though, again, as you can see here, the accelerations both were aiming to the right. So if I put the friction to the left, do I know right now who friction is going to harm the most? Is it going to harm the most ACOM, or is it going to harm the most alpha R? I assumed just previously that it will harm a lot ACOM, but what if it actually harmed a lot alpha R, right? And we had alpha R flip direction while ACOM stayed on the other side, and again, they balanced out that way. It means basically we could have right now two scenarios, two outcomes from this friction's action here. And I'm going to outline them here. Here's what could happen, okay? We said that after we account for friction, one of the scenarios here is that, again, we're going to get a residual alpha R right now, forwards like this. And we're going to get over here an ACOM that points basically backwards like so. So this was one of the scenarios, right? We discussed it just right now. And another scenario, of course, is the exact opposite. So basically, I could have alpha R flip direction right now. So I could have here the roles switched, basically. So alpha R could be the one harmed a lot by friction, and I could have this scenario on to the right. So which one is it, right? Which one is it? Which one am I going to have? Is it something I can tell, you know, off the top of my fingers here? No. And what do I do when I don't know something, when I'm problem solving? I have to make a guess. So me being again me, and again putting together reasoning, I think that the right one seems more plausible for the spool again to move forwards from the action of this force F. So it seems more plausible that it will move forwards to the right rather than to the left. So I could be wrong. Regardless though if I'm right or wrong, I have to stick exactly to what the consequences of my decision are right now, if I am to even have a chance to actually solve the problem here. So I will choose to stick with this scenario, okay? So I will pick this up right now. I expect these things to happen, and I'm actually going to go ahead and solve. So I guess the scenario here again that this is going to be my case. Let me just copy here the arrows to show you. This is what I guessed. Okay. So that means right now I will have an overall angular acceleration that goes like this, and a center of mass, again, acceleration that goes like this. Okay. Put in again over here the actual forces back onto the spool. We're now going to actually solve the problem because we have everything. So I'm putting back here gravity acting in the middle. Okay, so that's capital MG. I'm putting back here the normal acting up from the contact point right there. That's going to be my normal. I have the force capital F that acts to the right here, like so. And I have finally determined what the correct choice for the friction should be. We know that regardless of what the outcome is for the accelerations, friction, in order for the accelerations to even have a chance to balance out, needs to point to the left here. Now, what kind of friction is this going to be? We haven't even pondered upon that. We know that this spool starts from rest. So if the friction is sufficient for us to immediately start rolling, we need to have basically enough static friction to get us those required accelerations to match here, the alpha R and the A com, to actually match from the get-go. As soon as the spool has that force F applied to it, we want the friction from the get-go to keep them balanced like this, the alpha R and the A com from the get-go. So there's never going to be a case where I was basically spinning way more than I was translating, so I skid or I slip. There's not going to be any of those possibilities. So there's never going to be any friction between the contact point and the ground, which means I'm always going to be providing my system with static friction. And that's exactly the situation here. We're going to have a static friction in hand. So how do we solve this problem? Well, the same way, again, I attempted to solve it previously. We're going to put down our forces over here in a little free body diagram right now. So I'm going to go ahead and draw you real quickly again these in a free body diagram. That's how typically I want to go about it, because there might have been involved angles here. And if that's the case, they look cleaner. Angles are very easily manageable in a point free body diagram like this. In this case, you could get away just by looking at this. So if we go ahead, we have guessed right now that the acceleration is going to be, for the linear, it's going to be to the right. So there's my guess, which means my positive right now, one of my directions needs to be along that, and the other one is for free. I'll choose it to go up because of that. So there's no acceleration right now in the y direction, but there is a force, again, from the normal and a force from gravity going against it. And that, again, gives me what the normal should be. In the x direction right now, we know there is an acceleration. That acceleration is A com. And F net x right now involves F, which is the applied force, minus the frictional force. And we're going to equate that again to MA com. The frictional force, though, you can replace, obviously, with a coefficient of friction times the normal. And then the normal itself, you can replace with what we found up here. So F minus mu S capital MG is equal to MA com. And very easily, you can divide both sides by M to obtain the linear acceleration here of the center of mass, which is going to be F over M minus mu SG. And there you have it. That is your linear acceleration right now, but we don't know in this problem the coefficient of static friction. We'll have to figure that out first. Okay, so that takes care of the linear world. Now we're going to go and assess the angular world. And in the angular world right now, we've talked about why the torque provided by the normal and gravity. Just before we said that these torques are going to be zero. So that remains the case here as well. So they don't contribute anything. And the torque from the force F here Again, remember, we're trying to fill up this equation, RF sine theta, for each of the torques. So once again, for the force capital F, the R vector has a size here, little r. So we're going to put in little r. The force is capital F, and the angle that little r makes, again, we can see here with the force F, is going to be 90 degrees, just like before when we were solving, without the friction. That goes to 1. Is this a positive or a negative torque? Well, we take a look again at what F is trying to do. And if you do the pen trick again that I was telling you to do earlier, what F is trying to do right now, in your perspective, again, it acts to the right. So it's trying to spin us counterclockwise. F, if we pin our pen again at P and apply F, it's trying to spin us counterclockwise. Counterclockwise, again, based on what we're seeing here, counterclockwise is not in the direction that the angular acceleration is going to be, right? Because acceleration, again, determines the sign that is positive. That's our rule. So if this is trying to spin us right now counterclockwise, well, clockwise is positive, it means this torque is going to actually be negative right here. As for friction, again, because it acts to the left, in your perspective, friction would be basically going this way to your R vector and would be spinning it, again, clockwise. So that means it would be a positive torque. And where is friction acting? The R vector for friction, again, is basically of size capital R, very obviously. The force of friction is F of S, and the angle, again, that the R makes with force of friction here is going to be 90. So that's exactly what I put in here. Okay, sine of 90, obviously, again, just 1. All right. So now all I have to do is just simplify this a little bit. I just realized that I started with the torque here just from F, but what I ended up doing was doing the sum of the torque from F and friction. So these are the two torques that are acting and are non-zero, basically. So when I want to fill in now Newton's second law right here, which says tau net is equal to I alpha, I also need the moment of inertia here of this spool. Now, over here, for my spool itself, typically you're going to be given the moment of inertia of that, again, system. If you're not, what you can do over here, what you can do is use, again, ratios of the mass from the outer spool and the inner spool, and that will help you, again, determine what the moment of inertia is. So for the problem here at hand, what I will do is I will allow you to use the moment of inertia as a given, because I don't want to spend too much time doing basically extra parallel axis theorem practice. So I'm just going to say that we have it already. If not, again, you can determine it with a little bit more effort, but I don't want to make this video too long unnecessarily. So I'll provide the moment of inertia here with respect to the rotation axis, which is, again, here in the middle. That is the center of mass, basically, here. So that, consider it provided, okay? Consider that it's being given to you. And we can go ahead right now and actually set up our problem. Tau net right now is basically only provided by these two torques, which we've already found over here. So the only thing that's on the left-hand side is minus little r capital F plus capital R FFS, and all of this is equal to I alpha. What I can do here next is open up the friction as mu s times the normal. Okay, so I will do exactly that. And of course, the next move here is to put in what the normal is over here. The normal is simply, we determine, is going to be capital mg. And then why not divide, while we're at it, both sides here by this I, so that we get basically the angular acceleration on its own. It's going to be m, let's write it like this, mu s mg capital R, and then minus f times little r, all divided by I. That is the formula for your angular acceleration. And you basically have both of them right now if you were given the coefficient of friction, which again, we're being mean here and we're not providing you with. So what I'm going to do to find the coefficient of friction, I know that from the get-go, I will be rolling. So what I want to do here is abuse that. And I know from the get-go that what is going to hold is that the linear acceleration will be equal to the angular times r from the get-go, from the first moment that we start moving the spool. So that allows me again to write basically this equation here. So this guy over here for the linear equal to the angular, which was this one, times r on the other side. So I'm just going to fill that in here for us. Okay. So what I want to do is solve for the coefficient, which is here and here. So I will have to inevitably open this up a little bit. So this is a little bit of algebra right now. So I'll have to open this up. I get mu s mgr over I minus. Don't forget here to distribute your r while you're at it. Why not? So we're going to get r squared there. And then for the second term, we're basically going to get these again together. F r capital R divided by I. All right. So the next thing I'm going to do here is I'm going to move this term over here, that term over there. Let's see again what happens. I'll factor outside the mu s while I'm at it. And I think I can factor outside here a factor of r. Actually, no, I cannot, sadly. That's all right. So what I'm going to do here is actually I'm going to factor a g. I wanted to make it fancier, but unfortunately, you can only do so much. So I'm going to factor outside a g while I'm at it. And it's going to look like this. We're going to have m right now, r squared over the moment of inertia. And then plus here, just 1. And on the other side, we're going to factor, we can factor f and end up with 1 over capital M plus here, plus r times capital R divided by I, just like that. All right, so we can cross multiply here to solve this and write the coefficient in a fancy way. So I'm going to have here mr squared plus I, if I cross multiply the left bracket, divided by I. And in the right bracket here, what I could do is cross multiply again. So I will end up here with I plus R times capital R. And then I'm going to divide here by M times I. And the I's here, you can see very quickly, they're going to go away. And all I have to do here is actually finally isolate for the coefficient of friction. So mu s here is going to be F over G multiplying over here, open bracket, I plus little r times capital R divided by mr squared plus the moment of inertia. And this is again the result to our part A, which was asking for that coefficient required to get us immediately rolling from the get-go. And now that you have that over here, you also have the equations again for the accelerations. You can consider that to be like 1 star here and 2 stars here. What we're going to do next is simply a plug and chug. So we're going to take the coefficient right now, so equation 1, and basically just plug it into the 1 star equation to get the angular acceleration. And if I do that, I'm just going to copy here because we're in OneNote and we can speed things up. Just going to copy what alpha really is right there. And again, we can just plug in right now what our coefficient ended up being. So right there in the numerator, I'm going to have to create a little more space right now because we're going to introduce this expression for the coefficient of friction right now. All right. So I'm just going to do just that. That's again what I will multiply right now, that first term by. So there's not a lot of simplification you can do right now when it comes to this. I can barely see anything that we can do ourselves here. The only thing I can see of is, no, not even, just canceling here this G, and that's about it that you can do. So in a clean way, you can write this as, if you'd like, as F, let's write it like this, M, F, R, and then we're going to have I again, basically the bracketed term. So I'm just going to bring it over. There's not much you can do after that point here to simplify this algebraically. It is what it is, right? And then we're going to take away, we can factor, I guess, here an F. I don't know if you guys would appreciate me doing that, but I'm just going to leave it like this. I'm not going to torture it too much. You know, we just want to make sure that we copied it correctly, and it looks fine. So that is, again, how you would get your angular acceleration right now, knowing the coefficient of friction and plugging it back. So the last thing, of course, that we wanted to determine is the linear acceleration. So you'd think that I would probably just take equation 1 and plug it into 2 stars right now, but there's a faster way than that. Recall that we're rolling from the get-go, so we obey this equation, right? We always roll from the get-go. So what you can do to determine ACOM is very simple. You just take this result here and multiply it by capital R. That's going to get you exactly what you need. So I can represent that by just introducing here a square and an R right there. That's going to be exactly my linear acceleration right now. Hopefully no algebra mistakes. And that's how we basically obtain all 3 of the requirements. Again, pay close attention when you're doing these kinds of problems on how the accelerations in the beginning look like, so you can determine the proper direction of friction. Look at what that means for the possible scenarios that you can have here for the accelerations. You can see how mine again look like this, either or. Pick one that you like and stick with it right now. So if I pick that over here and I stick with it, it determines basically all the positives that I'm going to be using in my diagrams, right? Because again, positives align with our directions of acceleration. And we really want to stick with that, because if we make the choice not to, in terms that involve 2 terms like this, in ACOM, for example, that involves 2 terms, if you don't stick with that choice of keeping those pluses consistent, it could say right now here mu sg minus f over m, which when you plug back here, when you plug back into this equation, if you plug it the reverse, you're going to get a very different thing for the coefficient of static friction, giving it the possibility to be negative under some appropriate choices of parameters. That's not what you want, right? You want to make sure that you stick with those positives. Again, depending on the scenario that you chose to guess, you stick those positives properly onto your diagrams and you follow the, again, your torques and forces follow those signs to the T. If you don't want to make a mistake of a sign here, and it's really easy to make one, that's why I'm stressing that so badly. So another thing I wanted to mention here, the reason I know that mu s here is probably correct, I'm not going to say 100%, because there's always possibility of an algebra error. I'm really confident though, because the units are correct. You're getting a unitless quantity, and again, I'll leave that as an exercise for you to confirm that you're getting a unitless quantity right now. And on top of that, this quantity has no possibility of being negative. You see, we're adding these terms at the top, we're adding them at the bottom. All of these constants here are positive, so there's no way we can be negative, and that's further confirmation that, again, we've applied those positive directions again correctly for the forces and then for the torques here, and we haven't made a sign error anywhere in our calculations. So I'll leave you with that, and I encourage you to try different orientations of the applied force over here. See again what happens if you give it a little bit of a vertical component as well. See how that changes what your force for the normal is going to be, and what the rest of the F here, basically what you're going to replace F in your equations with, right? So I hope you found this helpful. Again, spools are a very complicated topic, so it's again about time that someone shines light on how to think about setting it up and solving it. So I hope you found this helpful, and if you did so, consider, of course, following and subscribing, and stay tuned for more of these videos. Thanks for watching.